my series started. All right, so maybe it's because I don't know why. All right, so previously we talked about the univariate distribution. There was a lot of them, right? So both discrete, so binomial, hypergeometric, Poisson, right? And also for continuous, exponential, normal distribution. So variants of them, such as a beta distribution, gamma distribution. So for multivariate distributions, usually we either saying kind of, so let us look at several univariate distributions, so several univariate random variables, and assume that they're independent. And if we don't want independence, then our choice is actually much smaller. So there are only kind of maybe three interesting distributions. So interesting distributions which are multivariate. So one of them is a multinomial. Right? And this is a generalization of a binomial distribution. Right? So another is multivariate Gaussian or multivariate normal. Variate normal. Which is obviously generalization of a normal distribution, univariate normal. And another is called Dirichlet distribution. And it's generalization of beta distribution, so it's also continuous, but we will make kind of that, the book doesn't say much about this, and maybe I'll just mention it or maybe skip altogether. This is important distribution, but it's slightly different in that multinomial is a discrete random variable. So multivariate normal, it's a continuous random variable. And Dirichlet, it's a continuous, but it's unfortunately, it's not supported on all the space. It's supported only on the plane, right, on a part of the plane. So it cannot be described by the tools that we derived here. So there should be some additional, it can be described, but there should be some additional discussion about this. So, so we will talk today about multinomial and multivariate normal distribution. So what is multinomial? So multinomial random variable. So we are here looking at the generalization of the binomial experiment. So experiment, so it's n independent trials. Right? And so we kind of so here's the most useful examples that throw a dice, for example. So we do it n times, and the outcomes have k types. And so the k is some number. So in binomial experiment, we just have two types: success or failure. So here's, so again, the best example. So throws of a die. And so the outcomes would be here. And so 1, 2, 3, 4, 5, 6. So this is something which we learned from the beginning, right? So finally we have a tool to describe this. So this is outcome. So so you can think that kind of outcome type 1, outcome type 2. So this is 6 possible types of outcomes. So k is equal to 6 here. And so now, so, and we do it some number of times. So, and Third assumption here, the probability of outcome type I is pi. So type I is pi. And so here would be, so in this example, this would be P1. So this is a probability that we have an outcome of type 1. So this is will be probability that we got type 1. So P2 would be probability that this particular throw will give result in 2 and so on, right? Until P6. It's probability of 6 in this example. Right? So now if you look at this, so this PI must be, of course, satisfy equality. So this is total number of types. So kind of they should sum to 1. Right? So this is just a size. So it must be that P1 plus P2 plus so on plus Pk is equal to 1. So these are all possible outcomes. Right? Now, this is experiment. So this is what we're kind of doing. And what's the random variable? The relevant random variable. So here is actually, since we are looking at the multivariate distribution, here will be k random variables. So it would be x 1. So it will be kind of x1, x2, and xk. So we did this experiment and we'll get this bunch, and xi will be just the number of the cases when we'll got the outcome type I. Xi is the number of outcomes of type I. So now again, so if you look at this kind of experiment, so what would kind of be in this case? So we could get, so n, say n is equal to 10, right, in this example. So we could have something like that: 2, 1, 2, 3, 6, 6, 4. So this is the 5. So say 1, 2, and 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this is a result of experiment. And so our experiment resulted in this outcome. So this is our omega. Right? This sequence of what's exactly the value on the die in these 10 throws. Right? And after that we say, okay, x1 here is equal, so there are only 2 ones, so it's 2. X2 is equal to 1, 2, 3, 3. X3 is equal to, so it's just 1, 1, so 1. X4 is equal to, again, 1. X5 is equal to 1, and x6 is equal to 2. So this is a value of our vector. So kind of our random vector here is a 6-dimensional vector, and this is the value of this vector in this particular experiment. So it's value of this random vector in this experiment. So now let us check. So 2 plus 3 plus 1 plus 1 plus 1. So 10, right? So it should be. So this x1, x2, xk, they must be also satisfy this equality. So they are not totally independent, right? So if you know 5 of them, you know the 6th one. So you know that in this example, x plus 1 plus x3 plus x5, so x plus 1 plus x2 plus plus x6 here should be equal to 10, right? So in general, you also have this constraint. So x1 plus x2 plus xk should be equal to n. So x1 plus x2 plus xk should be equal to n. Right? And again, so this is just a kind of just one random vector. Now, after that, the question is, what's the distribution of this vector? Right? So since this is kind of with equality holds, it's obviously that they are not independent. So if you kind of know 5 of them in this example, you can predict the 6 with certainty. So they're clearly not independent. Right? So we'll need to somehow figure out what's the distribution. Right? Right? So now it's in principle, it's kind of just an exercise. So it just kind of let me just sketch how you do it. So in general, you kind of, so it's like we did in the binomial. Right? So if you want to figure out what's the probability that x1 is equal to x1 small, x2 is equal to x2 small, and so on, xn, sorry, not xn, xk is equal to xk. Right? So here's a k types and n possible n trials. So parameter is n and number of trials and pi. So these are parameters of here. Now, if you want to figure out what's this probability, then we're doing basically the same stuff that we did for binomial. We look at some particular sequence which have a x1 outcomes of the type 1, x2 outcomes of the type 2, and xk outcomes of the type k. So for example, we could have a sequence 1, so 1, 1, right? And this is x1 times. Right? After that, we have a sequence 2, 2, and this would be x2 times. Right? And so on until the k, right? And this would be xk times. So you can think about kind of this throwing of a die. So in this case, xk would be 6. So 6, 6, 6, 6, and this would be x6 times. And so this is one possible outcome of an experiment. So we're saying what's the probability of this specific outcome? We're saying, okay, so this is a probability of this one was P1, probability of this one also P1, and so on, right? And they are independent. So probability to get this sequence of ones will be P1 to the power of x1. So just P1 multiplied by P1, so because kind of trials are independent. Probability to get 1 in the first trial is P1. Probability to get the 1 in the second trial is also P1. Okay, so you do it x1 times, and the probability that you'll get all ones is P1 to the power x1. Same thing with 2. So it will be P2 to the power of x2. So on. Here will be pk to the power of xk. So this is a probability of this specific outcome. Okay. Now, if it's not exactly kind of in this order, so maybe kind of, well, maybe it's a different order. Maybe all twos first and well ones after it. All kind of any permutation of this sequence of ones, twos, and other types. If you think about, well, it will be still the probability will be equal to this quantity. probability of this sequence just depends on how many ones you have, how many twos you have here. It will be always kind of, if it's the same number of ones, same number of twos, same numbers of k's, right? So the probability will be given by this expression. You just multiply things in a different order. Okay, so if it's kind of starts with 2, it will be P2 multiplied by P2, and okay, and after that you start to multiply by P1, P1, P1. So it doesn't matter in which order with ones and twos and k's. That's what's important, how many of them. For all kind of sequences in which there is x1 ones, x2 twos, and xk k's, will still be this probability. Right? And so, okay, so this specific outcomes has this probability, and all sequences in which this number of outcomes of type 1, this number of outcomes of type 2, this number of outcomes of type k, well, it will have this probability. So we'll just need to count how many of them. And then if you go back a lot of back, so we had a problem which counted how many permutations. So this is probably one of the first things that we did in this course. So how many permutation of a word in which we could be repetitions of the letters. And so think about these ones, twos, and k's as the letters. This is a word, and how many kind of different arrangements of these letters. Right? So, and we calculated in the beginning, of course, that this is given by something which is called multinomial coefficient. And so we just need to multiply this probability, but the number of these distinct permutations, and this is given by multinomial coefficient. And so we'll need to multiply by n. Here's x1, xk. And so this gives us this probability. So because it's kind of probability of every sequence is this one, total number of such sequences is this one. So you sum the probabilities, you will get this outcome. So, and just kind of remind you what this coefficient is, that this coefficient is equal to n factorial divided by x1 factorial divided by x2 factorial and divided by xk factorial. So, okay, and again, so it should be x1 plus x2 plus xk is equal to n. Okay, so now this is we calculated the probability of this multivariate random variable. So just to fix it, we say that just to fix the concept, we'll write it as a definition. Okay, so definition. So k component random vector x1 xk as a multinomial distribution so with parameters so n and p1 okay, so on pk, so p1 p2 pk, so it's also vector of the parameters. And this is just this formula. If it has PMF, if it has joint PMF, So this is a joint PMF of this vector at argument which is equal x1, x2, xk. So before that we looked at just two random variables, so our joint PMF had just two arguments. And here's the k argument. So it would be p, and so here's x1, so on xk, so x1, x2, finally xk. So you see that it's probably better would to be write the vector here, but for explicitness we write it's kind of in components. And also here depends on x1. So let me write x2, so on, xk. And okay, so it's equal to so to this formula, so it's n x1, x2, xn. So it's a multivariate, multinomial coefficient with n here and x1, x2, xn in the bottom of the coefficient, at the bottom of the coefficient, multiplied by p1 to the power of x1, p2 to the power of pn, so p2, multiplied by p1 to the power of x1, so maybe kind of another one, p2 to the power of x2, so on, pk, and here's a k, not nk, x1, x2, xk is also here, pk, xk. So, and so you can think again about this example with our dice, then will be x1, x2, and finally x6 here. And here's will be again, so p6 to the power x6. So in principle, our die is not necessarily fair. Right? But we'll need to specify, which is not always kind of, not for every x1, x2, xk. So obviously it should be integers, right? Kind of. So I will not write it that this is integer, but also kind of obviously that this should be greater or equal than 1. So xi should be greater than equal than 0. Otherwise, will this not be defined? But the most important thing that the sum of them should be equal to xk, so x1 plus x2 plus xk should be equal to n. Well, it's kind of obvious from the formula. And so if you plug in here something such that x1, x2, xk not equal, sum of this not equal to n, then this is not defined. This multivariate coefficient will be not defined. But if you kind of write it, so in the form like I write, it's kind of obvious. But if you write it as n factorial divided by x1, factorial x2, factorial xk, factorial, it's less obvious because you can, in this case, you can plug in x1, x2, xk, which sum of which is doesn't equal to n. And so this is all 0 otherwise. And so this is just kind of carefully that will kind of, it should be like this one. And so this is a definition of a multinomial distribution is defined by a joint PMF. So now also kind of it's a generalization of a binomial. So let us see how it's connected with a binomial distribution. So binomial distribution so binomial distribution so it corresponds to k equal to 2. If k is equal 1, nothing interesting, just one type and nothing happens. So it's always kind of one type. It's not random. Right? K equal to 2, so here's two types of outcomes, success and failure. And then previously we just counted successes. Here we also counted counts failure. So x1, so it's number of successes, right, and x2 number of failures. So parameters. So parameters is well n, right? And okay, so in this case P1, P2. So in our previous notation, so P1 is equal to P, so it's probability of the success, and P2 is equal to 1 minus P or Q. So right, so this is what we had. So now how about this join? So K is equal to 2. So in principle, kind of, well, it's still multivariate. So, so how come that we had a univariate, binomial distribution was univariate before, if K is equal to 2. If you look at this, then the joint density would be x1, x2 here, so forget about the K. Right? The joint density would give you, in case of a binomial distribution, it will give you P of x1, x2. Right? So in this case, it would be equal to, okay, so here's x1, x2. It would be equal to, so n x1, x2, and here's p, and let us use this thing. So p to the power of x1, and here's a q to the power of x2 in principle. But this is only true if x1 plus x2 is equal to n. And so what in this case happens that although it's a kind of multivariate, it's x1 and x2, but one of these random variables is completely determined in terms of the other. So x2 is equal to n minus x1. And so this probability, it depends not on the two arguments, but essentially on one. Right? So you can kind of remove x2 from here and write that this is just equal to n. So this multinomial coefficient is in fact equal to n and just here x1. So just kind of by definition, if you write down what's the definition of a binomial coefficient. So here will be p x1, and here you would get q, and here's n minus x1. And so this thing will depend just on x1. So everything in determinants of terms of x1, so we can kind of forget about x2 and talk only about x1. This is what happened when we talked about binomial distribution earlier, and so we said, okay, so forget about number of failures, because if we know the number of the successes, we can now figure out what's the number of the failures. And so in general, if you have 6 outcomes, well, you can, if you know 5 of them, you can figure out what's the 6th one. But it becomes not symmetric, which one you want to remove. So in principle, it's possible to write here everything in terms of the just k minus 1 types, k minus 1 variables x1, x2, and k minus 1. But it's not clear which one is preferable to exclude. So, well, you write it like this. Okay. Okay, so now, well, maybe another example. So, so this is an example. So players, so card players. Yes. And so maybe 3 card players. play 6 games. So, in a particular game, probability that player 1 wins, PA, so this is a probability that player A wins. So say equal to 0.2, okay, so 20%. And similarly, we can define PB, probability that player B wins. Okay, so this would be 0, say 3, and PC. So it's probability that player C wins. So here will be 0.5. So here's so 6 games. So we'll also assume that we're independent. So given the probability of wins for every player, and say, so ask the question, so what is the probability that A wins, say, 1 game, B wins 2 games, and C so wins 3 games. So okay, so this is an example of how we could apply multinomial distribution. So it's multinomial, classically multinomial, so 6 independent games. So parameter n is equal to 6. We are given probability of each outcome in a specific trial, so in a specific game, and after that ask the probability that you in this sequence will have some specific number of types of outcomes. So here's just kind of answer, just one line. So, so probability in this case, so this would be X and kind of, well, so say XA, so it's the probability XA would be how many games player A won. So XA is equal to 1, XB equal to 2, and XC equal to 3. So we want to figure out, so it's a multinomial distribution, and so here we have a 6 total number of games. Here's 1, 2, 3, right? And here's okay. So here we have a PA. Right? So PA is 0.2 to the power of 1. So let us kind of just 0.2 multiplied by 0.3. So this is the probability of the being of a player B to the power of 2 multiplied by 0.5 to the power of 3. Okay, so you put on the calculator and calculate that it equal to something. Okay, so this is a thing. Now, kind of I usually kind of think when we learned about the univariate distribution was saying what's the expectation of this random variable with this distribution, how it depends on the parameters, and what's the variance. So this was a basic questions. So in this case, we have several, so it's a vector So we need to ask about expectation of every component of this vector, and about the variance of every component of this vector, and maybe about covariance of different components of this vector. So here's a theorem about this thing. So suppose so here we have a random vector x1, xk. So and we assume that it's have a distribution, it's multinomial, and its parameters will be n. So sum of all this kind of x1, xk, and a vector p1, pk. So what we can ask? So expectation of xi. So, well, I'm going to prove that this is equal. Well, it's actually when kind of here's for a couple of these results, it's easy to just explain. Right? So now if you look at the expectation of xi, so let's look at x1, for example. So x1 is the number of outcomes of type 1. Right? So kind of in our example with the dice, it will be number of times when we'll go 1 as a result of a throw of a dice. And so let us call it as a success, and all other outcomes failures. Right? So now we have now we converted our experiment in a binomial experiment, and the question is so in a sense, we kind of look at the marginal distribution. So what's the marginal distribution xi? And we're saying, well, this is a kind of binomial random variable. It's binomial distribution with a total number of trials n as before, and probability of this specific kind of random variable equal to pi. And so probability that you have a success here is equal to p1 or pi. And so kind of p1, and if it's x1, in general pi. Right? Probability of that in one throw you'll get a type I. So all other things are, you call it, all other things are failures. So you're just interested in how many times you'll get the outcome of type I. So this is obviously kind of binomial experiment now, just successes and failures. This binomial experiments has a parameters n, the total number of trials, and probability of a success. Success, by my definition, is getting the outcome of type I. So it means that the xi is actually has a binomial distribution. As a single random variable, it's have a binomial distribution with the parameters n and pi. So, and I'll need to calculate expectation of this random variable, which I know kind of, well, as a single variable, the binomial random variable with parameters n and pi. So I know what it's equal n multiplied by pi. Just because there's a single random variable, this is a binomial distribution. So, and behind that, it's kind of also kind of something like I essentially calculated what's the marginal PMF of this xi. It's binomial PMF. And something in behind that. Well, and the same thing for the variance. So if it's just kind of one random variable, then the only thing that I need to know is what's the distribution of this single random variable xi. And I know it's binomial with parameters n and pi. So variance of the binomial random variable with parameters n pi, it's equal to n multiplied by pi and 1 minus pi. So n multiplied by pi multiplied by 1 minus pi. And so here's also pi. And so this is easy because kind of a multinomial, kind of a marginal distribution of a multinomial is a binomial. Marginal PMF of multinomial is a binomial PMF. And so this is not so very interesting. So what is more interesting, what's the kind of covariances? So the only next thing which might be interesting is covariance. So what's the covariance of xi and xj? And here I cannot do this thing because here we are talking about really about two different random variables. And we know that we are not independent, so I cannot say we are independent, so covariance is equal to 0. So I really need to calculate this thing. And so, and as far as I remember, it's equal to minus n pi I pi j, but we'll need to calculate, it's not obvious. Right? So first of all, it's kind of more or less obvious that it's minus, because we know that if you have very many outcomes of the type I, then it should be that not so many of outcomes of the type J, because we kind of eventually we should sum to some fixed number, to n. And so we have that all of the outcomes of type I, then there is no room for the outcomes of type J. So they're negatively correlated. And so there are many outcomes of one type, there are less outcomes of the other type. So this minus, you can guess that it is minus, but in general that it's this particular form, we'll need to do a calculation. So let me briefly do a calculation. So it's a little bit kind of has some notation, right? So, but it's easy. So proof of, so this is kind of 1, this is 2, and this is 3. And so proof of 3. And so now, remember we calculated variance in the binomial by introducing the indicator functions. And so indicator random variables, which are equal to 0 or 1, depending on whether you have a success in specific trial or you have a failure in specific trial. So we do same thing here, but we'll have here two different indicator variables, one for the outcomes of the type I and another for outcomes of type J. Right? So let me call it I, right? And say call it IS, right? So S here is the number of a trial, right? So and so what is by definition? So it's equal to 1 if in trial number S, so we got outcome of type I. Right? So then it's equal to 0 otherwise. And so we have our experiment, we have our sequence, right, of what's the numbers we went in every throw of the dice. So we'll look at the kind of, if S is equal to 2, for example, we'll look at what happened in the second throw of the dice. And saying, well, if it's equal to I, then this random variable will be equal to 1. If it's not equal to this I, so kind of it will be equal to 0. So it's clear kind of how it's defined. It depends on the outcome of the experiment, but so now what's good about this, right? So what's good about this random variable is before we can write that this xi, so xi, so it's the number of the trials in which we got outcome I. Okay, so if you throw the dice when and I is equal to 1, then it will be number of times in which we got 1 in these throws of the dice. So and it's equal to I1 plus I2 plus so on plus IN. So kind of this is equal either to 1 or 0. It's equal to 1 if we got I in the first trial. Right? So then, okay, so we counted. If this I2, I large 2 is equal to also to 1 or 0, it's equal to 1 if we have an outcome of type I in the second trial. And so on, kind of you sum all ones, we'll get the total number of outcomes of the type I. Okay, so this is, we did it before. Right? So the only difference here, we also define another one, right, for the outcome of type J. So we define, so let JS, so another one. Okay, so and it will be exactly the same as here. So it's equal to 1 if in trial number S, we got outcome of type J. So only if you have a difference here that this is kind of, it's equal to 1 if we go to the outcome of type I, and here it's equal to 1 if we got the outcome of type J. Now, and we kind of, when we do this thing here, so, okay, so this is actually not right. So what is this statement number 3 is not exactly right. So we also need to write here that it's I not equal to J. Otherwise, it will be variance of xi, and this formula would apply, not this one. Right? So here's I not equal to J in the third formula. And so we always assume that this I and this J are not equal to each other. And so, okay, so here we'll have it xj is equal to j1 plus j2 plus jn. And so now, so this j kind of, well, kind of, you can think about 1 or 2 or something like that. They are fixed. Right? So these types are fixed for our, just kind of for generality, I call it. Right? So it's slightly maybe confusing because we have a lot of kind of i's and j's. So this I is fixed. Right? So j is fixed. Right? This I1, I2, IN are random variables. J1, J2, Jn are random variables. Okay, so now after that everything is set up and we just do a calculation, this is a little bit kind of, well, cumbersome calculation, but not very much. So we just need to calculate this covariance. Right? So covariance of xi, xj is equal to expectation of xi, xj minus expectation of xi multiplied by expectation of xj. Okay, so now, okay, so we actually know expectation of xi. It's pi multiplied by an expectation of xj. It's pj multiplied by n, by our theorem. We already know these things. So we'll just need to calculate expectation of this product. And this is where these formulas come handy, because otherwise we don't know how to do it. Okay, so we otherwise will need to write a big formula with this PMF, joint PMF, and try to figure out from this big formula for the joint PMF what is this thing. This would be really kind of hard. Okay, so with this trick, when we kind of split everything in an indicator function, it's much easier. Okay, so this is kind of, well, slightly tricky proof because it's uses, you need to use this. Otherwise it would be if you apply this formally, this would be difficult. All right, so what is expectation of xi xj? Okay, so let us plug in these formulas. And so since I don't want to write always kind of I1 plus I2 plus 3 dos plus IN, I use summation psi. Okay, so this is kind of slightly shorter. So AI S, where S changes from 1 to N. Right? And it should be multiplied by another sum of J, say T, where T is from 1 to N. Okay, so this is I substituted this thing here. Right now, so now here's mostly for people who enjoy kind of proofs. Okay, so now what you are doing, kind of, you're looking at this thing and saying that first of all, it's kind of, it's equal to, okay, so I forgot expectation here. So expectation. And after that you, okay, so you multiply it, so you'll get sum over, and here we'll just write S and T. So S, both S and T, they run from 1 to N. So just let me write S and T. Then IS multiplied by JT. It also expectation. It's linear. So we have expectation of a sum. It's equal to the sum of expectation. So we can put expectation here. So now we basically need to calculate what is expectation of IS multiplied by JT. Right? Maybe I shouldn't remove this definition, but right. Okay, so now here's what we have. So we have the trial. So here's S, here's T, here's so kind of 1, kind of 2, at some point S, and finally N here. Okay, so now so IS and I and JT. So it can take values either 0 or 1. Right? So because IS only 0 and 1, and JT is also takes the values 0 and 1. Right? Now, so we're interested in expectation of this random variable. Right? So expectation of this random variable. Now, if you have a random variable which takes value 1 and 0, and you want to take expectation of this thing, so it's equal to the probability where this variable is equal to 1. Right? So, because what is this? When you took expectation, it's the value 1 multiplied by the probability of this value, plus 0, value 0, multiplied by probability of 0. But 0 multiplied by probability of 0 is totally not interesting, because it's 0 multiplied by something, it will be 0. So it's equal to the probability that IS JT is equal to 1. And so this is kind of much nicer, because we'll just need to calculate the probability that IS multiplied by JT is equal to 1. Right? Instead of calculating expectation, which is, no, what is expectation? We'll need to calculate probability, which is kind of easy to handle. And so after that, we are saying, okay, so there are two cases here. So first case, when S is equal to T. So everything happens on S on the same trial. But in this case, you are saying, okay, this cannot be equal to 1. Because I and J are different things. You cannot both have I in this trial S and J in this trial S. So this IS is equal to 1 only if you have in the trial S outcome is equal to I. J, well, and if this is also an S on the time S, it's the equal to 1 only if you have outcome of type J. If I not J, and we assume that I am not equal to J. If I'm not equal to J, it cannot happen both. So if S is equal to T, that this probability IS JT, so here's, okay, S is equal to T, so this JT is equal to S, is equal to 0. They cannot happen both. On the same time. And so now second thing is more interesting kind of, and so we're asking what's the probability when S not equal to T. So now it can happen. So you're asking here the probability that this product is equal to 1. It can be equal to 1. And so it can be equal to 1 only if both of them are equal to 1. So it's equal to the probability that IS is equal to 1 and JT is equal to 1. And so only in this case it's equal to 1. And after that, okay, so you're saying this is the probability that when these things are independent. And so you can write that this is equal. So the trials are independent. So this is the same as the probability that IS is equal to 1 multiplied by the probability that JT is equal to 1. So the probability that in the trial number S you have 1. Sorry, the probability that in a trial S you have an outcome of type I. This means that IS is equal to 1. It's equal to PI. So with IS equal to 1, it means that kind of in the trial number S, you'll get an outcome of type I. So here we'll have a PI, and similar here, JT equal to 1. It means in the trial number T, you got an outcome J. And the probability of this is equal to PJ. So here's PI, PJ. Okay, kind of first step is done. We'll know how to calculate this expectation of a product of IS multiplied by JT. It's equal to 0 if S is equal to T. It's equal to pi I pi J if S not equal to T. So now we are returning back to our formula because here was a starting point. We didn't know how to calculate this thing. So now we know. We know that S is equal to T when this is 0. If S is not equal to T, this is PI, PJ, and you know, PI, PJ, it's I and J is fixed, so it's just some number. It doesn't change, kind of, right? So some P1 by P2, kind of, right? Or something like that. So just something fixed doesn't depend on S and T, on anything, kind of, so everything the same. So you just not need just to count number of times, so number of possibilities when S not equal to T. So in this sum, so S changes from 1 to n, T is changing from 1 to n, and S and T should not be the same. Okay? So you have something like 1, 1, so it's excluded, right? So it's not possible. Right? You have a 1, 2, it's possible. Right? So this is outcome in the sorry, what I'm saying now. Yeah, okay, so kind of, yeah. So S is something like yeah, okay, so yeah. So S is something kind of from 1 to n, T is something from 1 to n. So all possible numbers of S and T, if you would depose the condition that they are not equal to each other, would be n squared. Right? N possibilities for S, n possibilities for T, right? Altogether n squared possibilities. Okay, so, right? But we'll need kind of to remove the things when S is equal to T. Right? And there are n such possibilities. So kind of it would be something like 3, 3. So S is equal to 3, T is equal to 3, you should remove it. And so 1, 1 should be removed, and n should be removed. Right? So from this sum. So there are only n such pairs. 1, 1, 2, 2, 3, 3, and n. And so you'll need to subtract this n because in this case, for this S and T, this thing is equal to 0. Right? Okay, so This is equal to n squared minus n multiplied by pi pj. So far, so good. So, well, and after that, well, we are done essentially, right? So we calculated this expectation of x, xj, and after that, well, we just apply this formula and say the covariance of xi, xj is equal to, okay, this thing, n squared minus n pi I pi j minus, and here this product, right? So expectation of xi, which was n multiplied by pi by our result number 1. And here's n pj. So you see here's n squared pi pj, here's n squared pi pj. So they cancel out. Right? So what remains is this minus n pi pj. So, okay, so this is the end of the proof. We have found the covariance. So this is very nice example of the calculation using this indicator random variables of some. It's an example of something which would be not so easy to calculate in our way. Just by, if we started by doing it with definition, well, we would have a very difficult kind of it's in this case it's one would need to calculate the yeah, we will have a difficult proof. In this case we would need to say that what's the marginals of this multinomial distribution, right? Marginal when we restrict to the component xi and xj, so it would be just component xi and xj, and okay, so this would be kind of like that. Okay, so this is a kind of, so this is a just first thing that you would do with multinomial distribution. After that, there are some things which we kind of will not maybe cover, but so just kind of so some other so just kind of to save it in this case, it's actually the number of equation is larger than kind of in the case of univariate distribution. We're basically done at this stage. So we calculate expectation variance, maybe moment generating function. In the case of the multivariate random variables, there are equations like that. So suppose that x1 x k is multinomial with parameters n, x1, xk, right? And so suppose that we learned something about of one of these random variables. Suppose somebody told you that so in our example with the throwing of a die, suppose that somebody told you there was a kind of some specific number of cases in which you had a 6 as a result of this throwing of a dice. So the question, how it changes the other distribution. So it's basically the question about the conditional PMF. So this question we didn't have before. And so now, what is the PMF? So conditional PMF. Of x1 so on xk minus 1 given that xk is equal to some specific value xk small. So this is an example of a question. And well, we don't have kind of time to kind of cover this question. So maybe I'll write the answer for this question, this particular case, but this is just kind of to illustrate that in principle, kind of the range of the question is larger in this case than the univariate random variables. Right? So it's a kind of more interesting situation. Now, so for this specific question, the answer would be something like that. So the interesting thing that it will still be multinomial. So this is one of the beauty why multinomial distribution is useful. If you look at the marginal distributions, so distribution restricted to several of this variable, or if you look like conditional distribution like that, they are still multinomial. So that means that if you calculate something using computer or anything, then if you do it conditional, you need to calculate conditional, it will be still multinomial, you just need to figure out what's the parameters. And kind of this is much easier than finding what's the new distribution. So in this particular case, the answer would be the conditional PMF is multinomial with parameters so first parameter is easy. So you know that you have n trials, and in xk of them you'll get the outcome k. Right? So for remaining outcomes, the number of possibilities, so the sum of them should be n minus xk. So n was the total number of the trials. And so x1 plus x2 plus xk should sum to n. Now you're kind of saying, well, I know already one of them. What about others? Some of the others should be n minus xk. So this is clear. And after that, the interesting thing, what happens with the other parameters. So it turns out that parameters will be the same as before. So it's p1, pk, right? So pk minus 1. Right? But now we don't sum to 1, so something wrong with these parameters. We must sum to 1. It should be like a probability. And you just divide it, kind of, you just normalize it. You divide it by p1 plus so on plus pk minus 1. So this is just, it's not any kind of explanation of a proof. A proof is you need to prove it, but it's kind of explanation of what's going on. And this is a simple thing which is going on. So its parameters will be the same, but just scaled such that they sum to 1. P1 plus 1 plus pk minus 1. Right, and this is okay. So again, interesting thing which happens in the practice. So this is one of the most useful thing. This distribution is one of the most useful thing in modeling, in statistics, and so on. And so now another example. So we're running out of time. Another super important example is a multivariate normal distribution. So okay, Okay, so multivariate normal. So now kind of to motivate it, just kind of just a reminder, what was a univariate normal? What's the density of univariate normal? So X is normal with parameter mu, and here's sigma squared. So if X has density right, so density is kind of 1 divided by 2 pi sigma squared. So square root of all this thing. Here's exponential, and here was minus x minus mu squared divided by sigma squared. So 2 sigma squared. So this was the density of this distribution, and it turns out that this is very important distribution. And so now, okay, so let us think about what happens if x and y are normal and independent. So now let us look at first of all case when they're independent. So now, okay, so maybe kind of we'll write it something like that. So x is normal with mean mu x and variance sigma x squared, and y is normal with mu y and sigma y squared. Now, okay, so this is easy. So this is easy case, because in this case, if we want to write a joint density, then you just take a marginal density of each of the variables and multiply them together. So you have it that x, y, so f of, so this was f of x, x, right? And here will be f of x, y, x, y. So, okay, just multiply this thing. So what we'll get after multiplication? We'll get something like which is 1 divided by 2 pi sigma x squared multiplied by 2 pi sigma y squared, square root of all this thing, multiplied by, let me write this as an exponential. So this is e to the power of minus thing. So it's like, it's kind of not, it starts to become cumbersome. Let me write exponential, which is the same thing. And here's minus, here's x minus mu x divided by 2 sigma squared x, here squared. And well, product of exponential is the sum of exponential, so minus y minus mu y sigma squared divided by 2 sigma y squared. Okay, so this is a kind of, with two random variables, normal random variables, independent, and here we have these parameters. Right, so formula is already kind of cumbersome. So now the question becomes, okay, so suppose that they are not independent. And what exactly this means? So, right, so you need to generalize this formula somehow, right, to include the possibility of not independence. So how you can generalize this formula? So you look at this is x minus mu x squared, here's y minus mu y squared, right, divided by some coefficient, and the natural thing would be kind of say, all right, so let us include something like x minus mu x multiplied by y minus mu y, and some coefficient here, so c. Right? So just include this thing here, right? And this will give you not the normal the multivariate normal, the general multivariate normal. So, but there are two things here. So first of all, it shouldn't be any C. So kind of you need to somehow explain what this C means, and maybe kind of it's kind of this should be density. Right? So you need to ensure that the integral is equal to 1. So it probably will change the coefficient here. Right? So this coefficient should probably will be different, right? If you include this thing. So, but kind of this is important step that you do. Just include this thing, and after that you will need to think about how the coefficient changes and what the interpretation of all the coefficients. So this is a motivation. So this is kind of the motivation. This is kind of what's it. And after that, well, you need to have some efficient tools to deal with this. And it turns out that in this case, the most efficient tool is come from linear algebra. So it is possible for two variables to write down everything kind of without linear algebra. But with the formula, it becomes super complicated. Okay? So kind of, since I'm just explaining things, this is nothing kind of, well, kind of which you need to remember or something like that. So, well, you can look in the book and see what's the coefficient in these new things, what is C, what this kind of, this is also will be changed. Okay? So, but now suppose you have not 2 random variables, but 3 random variables, which is a kind of normal, and you need to kind of to write these formulas. And so if it will be 3 random variables, you would need x minus mu x squared, y minus mu y squared, z minus mu z squared, and so in kind of all the cross products, and it will be very kind of complicated. So now let us look if it is possible to do it something like using the language of linear algebra. And so here I'm assuming that you know about the matrices. So, and well, so yeah, so if you take Calc 2, you probably know, so Calc 3, you probably know something about the matrices. So the only thing that we'll need is a kind of the concept of a matrix and the thing that it exists. The thing that concept of a matrix, concept of its inverse, and concept of a determinant. So, okay, so so suppose, so kind of, so maybe kind of it's actually definition. So definition. So, and now I restricted to 2 random variables, still restricted to random variables. So a multivariate normal so maybe sorry about this. So x and y, random variables x and y have a multivariate normal distribution parameters right, and so here will kind of this will be mu, so this is a vector. Okay, so parameters will be vector and a matrix. So mu, it's a vector which consists of mu x and mu y. And the meaning of this mu x and mu y is that with an expectation of x and expectation of y. Right? And so another thing we'll call it sigma. Right? And this is something which is called covariance matrix. Right? So what is this in this case? It's sigma x squared. Right? And this is the meaning of this thing is a variance of x. Right? So now it's not known, but it's possible later to prove that this is variance. And here will be sigma xy. This is the meaning of this thing will be the covariance. But in general, kind of here's any number. Right? So now sigma yx, and here's sigma y squared. So sigma yx, but we can also kind of sigma xy because this is a meaning of a covariance. It's equal to this covariance of y and x, and xy is equal to each other, right? So this is two numbers. And so now mu is arbitrary, sigma is not arbitrary. It's something which is called positive definite again. So I rely on maybe you learn about something like a positive definite or non-negative definite in Calc 3. So maybe kind of not saying so. Kind of it will be automatically positive definite if this will be variance and covariance. Right? So it's a positive definite matrix. So now, okay, so we have this matrix. So now I'm writing something formidable. So kind of so this if it's joint PDF, so joint density in this case, before we have joint PMF, here's joint density. So f of xy, so here depends on x and y. Right? And now first thing is kind of, it's something similar to what is written here. It will be 2 pi, right? And here, well, something less similar, this will be determinant of this sigma, matrix sigma. So determinant is, as you know, sigma x squared multiplied by sigma y squared minus sigma x multiplied by sigma x y. Right? So determinant, so well, here you have a sigma x squared multiplied sigma y squared because there was no covariance here. Right? And well, not square root of this, okay. It's so 2 pi to the power of 2 pi, so it's two-dimensional in this again, 2 pi, and here's the square root of this thing here. So it's just kind of, this is 2 pi, square root of 2 pi multiplied by square root of 2 pi, so it's given here 2 pi, and here's square root of this determinant. So this product of the sigma x squared, sigma y squared, but it's corrected, it's subtracted something from this. Right, and after that, so here's exponential. Right, so I'm writing this formula, but I want to write it something like a, so here's, let me keep it, x minus mu x, y minus mu y, but it's kind of, it will be something like written in terms of a vector. So it's minus 1/2, and here will be strange thing. So here will be so vector z, let me call it vector z because I don't have any choice, but I call it something like not x and y, but something. So vector z is with x and y. It's vector with components x and y. So vector z minus vector mu. And so now when vectors I think about, usually I think about row vectors. Right? Sorry, column vectors. So you need to transpose it to get a column vector to make sure that everything multiplies. And after that, it multiplies by inverse of this matrix sigma minus 1. And again by z minus z vector z minus mu. Right. And so here's a vector, it's a raw vector, so it have a kind of, it's what is written here. So this is z minus mu, it's a vector with the components x minus mu x and y minus mu y. And so this thing, here's this vector. And so here's also this vector, but it's a column vector. Here's a matrix which is inverse of this matrix. It's a covariance matrix. And so this is a result. Okay. So now what's the kind of beauty of this approach? So now if I say kind of let us look at the vector of the random variable which have not 2 components but 1,000 components. And so now this is, forget about this, you cannot kind of write it. So maybe you write it with some kind of a sums, you can write it with the sums, right? But okay, so not very nice. But here, well, don't change anything kind of. So this is just this matrix will become a 1,000 by 1,000 matrix of the covariances, of the variances and convariances. This vector will become a vector with 1,000 components. But when you write it, well, you don't see it. You will see that this is a matrix. Well, 1,000 by 1,000, but kind of notation is just one matrix. Here is one vector. So this is kind of this is why it's good. Right, and again, kind of you can write it down in this form. So you just need to invert this matrix. Right? So just kind of maybe to see that this is not kind of so kind of difficult, right? So sigma minus 1, so it's inverse of this matrix. So we go into the linear algebra and say what's the inverse of the matrix, right? So this matrix, we are saying that this is equal to 1 divided by the determinant, right? So determinant here is sigma x squared multiplied by sigma y squared, minus sigma xy squared. Okay, so this is the determinant of this matrix, and after that, here what we'll have will be sigma y squared, sigma x squared, and here's minus sigma xy minus 2 sigma xy. Sorry, not 2, minus sigma xy minus sigma xy. Okay, so this is kind of, if you have this matrix, you can plug it in this formula and calculate this more explicitly, getting something like that, which is again, so you can look up in the textbook, which is kind of, it's written in terms of the sigmas and the correlation coefficient. Right, so usually kind of in the more advanced courses, this is kind of the beginning of the game. Okay? So the beginning of the game, because once you you define it like that, okay? So you're supposed to know very well how to do the manipulation with the matrices, and you are starting to ask the questions. So what's the variance? What's the covariance? What's the expectation? So kind of just starting from the definition of the joint density, you'll find out that the expectation is equal mu x and mu y. So variance is equal to the sigma x squared, covariance is equal to sigma xy, starting from the definition. So you figure out this from the joint density. You figure out what's the variances and covariances with the degrees kind of this thing. So next after that is even more interesting thing. You're something what's the marginal distribution and what's the conditional distribution. Everything here will be play on the kind of on this definition and kind of how you do it. So the most important fact will be kind of that all marginal distribution and all conditional distribution will still be multivariate normals. Okay, so like for multinomial distribution before, multivariate Gaussian is most good because if you do conditional distribution calculate, it's still from the same class. You just need to figure out what's the sigma, what's the parameters for this new distribution. So this would kind of, but it's a beginning of a more advanced game. So it's a more advanced class which would treat these things like that. But okay, so these two distributions are most important. Another one is Dirichlet, but I don't have time to cover it. It's